Imagine a flood rising through an ant colony. The usual story is that thousands of fire ants cooperate, lock legs, and build a boat. But the first thing these ants do is almost the opposite. In a laboratory experiment, a small group on water flailed, kicked, and broke apart. Then, around 10 ants, the behavior flipped. A raft could stay together. The surprising part is not that ants can cling. It is that a simple physical force can create the beginning of a living boat before any leader, plan, or obvious teamwork appears. These are red imported fire ants, Solenopsis invicta, a species native to the flood-prone Pantanal wetlands in Brazil. When water reaches a nest, the colony needs a structure that keeps workers and brood at the surface, while the flood carries it. A Georgia Tech study recorded rafts assembled from hundreds to thousands of ants in minutes. The raft is not a wooden hull. It is a moving mesh of animals. Start with one ant. Its body is denser than water, but its waxy cuticle repels water, and its feet can ride the surface tension at the air-water boundary. That works at millimeter scale. The difficulty is obvious. Join thousands of bodies, and you might expect the whole mass to sink. The escape route is to link the bodies without letting water fill every gap. The researchers found that the raft traps air among the ants, turning a colony into a rough, water-repelling surface. Now watch the part that breaks the teamwork story. In the 2022 study, pairs of fire ants placed on clean water did not seek one another. They walked in random loops, flailed their legs, collided, and often departed in opposite directions. The paper describes this as active repulsion and exploration. So, if a raft forms, it cannot begin with a simple command that says, "Everyone move toward the center." Something else must beat the pushing apart. Each floating ant makes a tiny dip in the water surface. A nearby ant makes another dip. The curved surface creates a capillary pull. The two small objects slide down each other's slopes, like cereal pieces drifting together in milk. This is the Cheerios effect. It is not an ant intention. It is a physical attraction generated by the water. The ants can still kick one another away, but the larger the cluster becomes, the harder it is for an outside ant to escape that shared depression. That competition creates a sharp threshold. Coe and colleagues filmed 72 experiments with groups from 2 to 158 ants. Fewer than about 10 ants usually disintegrated within 5 minutes. The best fit critical size was about 9.3 ants. A 5-ant raft visibly broke apart over roughly 100 seconds. In their model, the transition appeared from 4 ingredients: random propulsion, water drag, repulsion when ants collide, and capillary attraction. No invisible group mind was required. Once enough ants are together, a second layer of physics and biology takes over. Fire ants grip one another with mandibles, leg claws, and adhesive pads. Their interlocked bodies trap air pockets, and the whole raft becomes more water-repellent than an individual ant. In the 2011 measurements, those trapped air pockets cut the mean density of the raft by about 75%. The colony has not made each ant lighter. It has made a new material whose voids are part of the flotation. The raft also behaves less like a pile and more like a living surface. When researchers removed ants from the top, ants from below moved upward and preserved the average thickness. The same bodies can be passengers, structure, or moving repair crew. That is why the raft can spread from a compact ball into a pancake shape in roughly 100 seconds, then keep its boundary while individual ants circulate. It is self-assembling and self-healing, but not because every ant sees the whole plan. Floodwater is rarely still. In a later Georgia Tech water tunnel study, a raft held against an anchor in flow of 6 centimeters per second gradually elongated from a circle into a more streamlined shape, roughly doubling its aspect ratio, before contracting again when the ants became less active. The researchers' fluid model associated that shape change with about 48% less drag. Ants in the high-stress upstream region explored less than ants downstream, suggesting that local movement helps the whole raft reconfigure. So, is the fire ant raft teamwork or physics? The honest answer is both, but at different layers. The first stable cluster can emerge from water surface tension, overpowering random repulsion. The large raft then adds grips, trapped air, and active rearrangement. The 2022 model does not prove that fire ants never communicate. It shows that we do not need to assume a social attraction force to explain small raft cohesion. The useful lesson is broader. When a crowd behaves like a machine, ask which job is done by signals, which by geometry, and which by the material itself. For fire ants, the boat has no captain. The rules are distributed across every body, every contact, and the water beneath them.